All right. Welcome everybody to the CSL Space and Astronomy Colonial this week. I'd like to begin it by acknowledging the traditional owner of the lands we are meeting on today and pay my respects to the elders past, present, and emerging. And today we are very happy to have Jim Level to talk about an adaptation of radio interferometry techniques to bioacoustics. Hi, Jim. All yours. Please take it away.
Okay, thank you very much. I thought a few months ago there was a symposium organised to mark the anniversary of the discovery of the AGN scintillator 0405-385, and also to remember JP Marquardt. And I was part of a collaboration that JP was involved in called Massive, which was a big scintillation survey with the VLA. And I was going to give this talk at that meeting, but we ran out of time, and it's expanded a bit since then, and I think I can probably fill the 25 minutes or so and tell you a bit about what I've been doing over the last few years in using my experience in interferometry to sort of move it into a different direction into bioacoustics. So if you've only been around playing this game for the last 10 years, you may not have heard of me. So I thought I'd give a quick background as to where I've come from and where I'm going. And those two gyms are nothing to do with me. The one on the right, sometimes I get emails and Twitter posts asking me for autographs and things, which is quite fun. But yeah, he's 40 years older than me. This is sort of a one-page summary or two-page summary of what I've been up to for the last 20 odd years. So I did my PhD at UTAS and with Dave Jauncey, who's on today. And my PhD project was in AGN variability and gravitational lensing in the radio. So the photo on the left there is the 26 meter at Hobart, and the object that I studied the most was Parkes 1830-2 on 1, which is a beautiful Einstein ring gravitational lens. And I did a big survey with the compact array looking for more, and unfortunately didn't find any. Following that, following my PhD, which I completed in '97, I spent a couple of years in Japan on a postdoc working with the VSOP Space VLBI mission. And then came back to Australia and worked in Canberra for almost 10 years at CSIRO ATNF in the Canberra office. And that was partly a support role at Tidbinbilla, and also my own research as well. It was quite a big overlap with that. So more interferometry, and that big photo on the bottom right is the VLA doing some observations for the massive scintillation survey, which was a huge amount of fun and very productive. So my background is mostly radio interferometry, tinkering with telescopes, making them do silly things like pointing in 5 different directions at once, and sort of the data analysis and processing that goes with that. So at the end of 2006, an opportunity came up to go back to Tassie, which is where I grew up. And we all, my wife and I and kids all moved down to Hobart in 2006. And I spent the next 10 years working on the Ozcope VLBI project, which is a geodetic VLBI array, which you may or may not have heard of. I guess you probably have. I was responsible for that, for constructing and commissioning that array and then eventually managing it. So we built and operated, and they're still going, 3 12-meter antennas for geodesy and astrometry. And that map on the right-hand side there shows where they are. There is one in Hobart, one in Katherine, and one in Yarragadee. And there's some photos of the real ones on the left there. So that was the project I worked on until 2017. And hang on a tick, I've got a window here, which hopefully you can't see. All right. And if I wanted to summarize what Ozcope achieved over those 10 years, this is a good map of that. So on the left-hand side is, at the top is the amount of, the blue dots show where the geodetic array telescopes are in the world in 2006, and the size of the circle indicates how much use they were getting. And the bottom plot shows the reference frame survey sources and the size of the dot shows how many observations were made. And you can see a very strong northern hemisphere bias. So on the right-hand side, you see where the Oscope array came in. So you can see the new antennas there, plus one in New Zealand, which Auckland University run. And we did a lot of survey work in the south, and you can see the improvement in the coverage of sky coverage and an improvement in the reference frame as a consequence. So that was the real sort of achievement, I guess, of Oscope. And it continues today, and there are upgrades going on and all sorts of other things. So that's where I came from. At the end of 2017, I made some changes. The job had become much more of a management role and not so much fun and research and things like that. So I decided to move on. And now I do some consultancy work on VLBI and telescope operations and automation. Currently have some part-time work with NVI, which have a contract with NASA for their space geodesy program. But also doing some volunteer work, and this sort of was a serendipitous sort of thing. There's a citizen science project which is run here in Tassie called Nature Trackers, and the family participated in their first survey in 2018, which is continuing annually, and it's a survey of the Tasmanian wedge-tailed eagle. And it's quite an amazing statistic and quite a sobering one in that of all of Tasmania's threatened species, only less than 15% are actually monitored. So nobody really knows what's going on. And the wedge-tailed eagle has been one of those, and using citizen science projects to improve that. So having participated in that project, I heard from Claire Hawkins, who runs the Nature Trackers program, that they were having trouble with the data and they were looking for help. And so I stuck my hand up, and that sort of snowballed into other things. And now we're running, I'm beginning to work on a third project, which is an acoustic survey as well. So as a result of that, came across this bunch of nice people who work in citizen science. The woman on the right-hand side at the top there is Claire Hawkins, who runs the Nature Trackers program. And as a consequence of this, I met that bloke on the right-hand side at the bottom, whose name is Stuart Newson. And he's from the British Trust for Ornithology, and he runs a big citizen science bat project. And he was telling me all about what they do and the recorders they used and things like that. And that got me thinking about how interferometry could be adapted or used in bioacoustics. So here's a picture of the sort of bioacoustics instruments that are in use at the moment. You have a majority of them just use a single microphone, and that and they record the time series, and they usually do a Fourier transform to extract frequency, amplitude as a function of frequency and time. And that's mainly for species identification, and they do some population estimates, although it's hard with a single microphone because you can see that there's a creature there and you can identify it, but you can't really say how many there are, if it's moving, what it's doing, but you can say if it's there or not. So you can do population estimates. And there's a lot of work going on in machine learning and AI to do automate the identification process, and that's mainly from this spectrogram. There are quite a large range of hardware. There's your proprietary professional level equipment, which is the order of $1,000 a unit. But there's some nice open source projects, and the most notable of that is this thing called an Audio Moth, which is an open hardware and software project. And they have a single microphone on a board, and you can pick up one of those online for about $150. So that's opened up a lot of research to organizations that don't have a lot of money or funding, and they've been using things like Audio Moths out there in the field, and putting out quite a lot of equipment. So that's the sort of the state of the art. But I was wondering why nobody does any multi-microphone recording, because you can do so much more if you use them as interferometers. So interferometers in radio astronomy are better than a single dish in many cases. If you cross correlate your telescopes, you get a great improvement in signal to noise, because all of the noise in an individual antenna is unique to that antenna, and when you correlate, all that, it basically goes away, and you're left with the signal, and which is good for radio astronomy because the signal to noise is much less than 1. And the delay in phase information gives you a direction to the source that you're looking at, and you can map it. So why don't biologists use audio interferometers? It's an interesting question. If you want to get a direction or a distance, then what has been done and is continued to be done is time delay on arrival, TDOA observations. So you have independent single microphone recorders at known separations, and you have to synchronize them in time, and and you have to be very precise with that, and that's a little bit tricky, but it's possible. And so you synchronize them all in time, you record those time series independently, and later you post-process them and measure the delays and reconstruct where the sound's coming from. There are other non-audio techniques out there, including thermal imaging, or you capture and tag the animal you're interested in and then do radio tracking. And they have advantages and disadvantages. Something like a thermal imager is good, but you don't have any sound unless you have a sound recorder that you've got going with it. So you can see that there's something there, but you can't necessarily identify it. Capture and tag is intrusive and a lot of work, and disturbs the animal you're looking at. And again, is quite a lot of survey work. You can't do that sort of radio tracking. Well, maybe you can, but it's much more difficult to do it in an automated fashion. So it's not widely used. It seems to be a little bit tricky, and it can be quite complicated to process the data, and the tech can be quite expensive. So why would you want to do it anyway? The advantages of localizing where the sound is coming from means you can identify individuals, which gives you much better population estimates, and you can see how the animal's using its environment, flight paths or movement paths, where it's living, nesting, things like that. You can do a lot more and really build up a picture of behaviour, as well as identify the creature in question. So this looked like fun, and so I, having spoken to Stuart and got enthusiastic about bats, I thought that might be a good place to start. So bats are practically are quite nice because they are ultrasound, so they're away from a lot of the other sounds. You get them up, they're pretty well isolated, and they're also very loud. If you could hear a bat calling, it'd be as loud as a smoke alarm. So you've got plenty of signal there. And the data is interesting because they're flying around and they're doing echolocation and very clever things, and you can say something about what they're up to, whereas a bird or a frog just generally sort of doesn't do quite so much interesting stuff. That table on the top right is sort of an interesting summary of the differences between radio and audio. It's interesting that the wave speed for radio, of course, is the speed of light, but the sound speed is orders of magnitude smaller. But when you take into account the frequency you're observing at, the wavelengths come out to about the same. So you're talking about centimeter wavelengths in both cases. Data for radio astronomy, for VLBI at least, is typically 2-bit sampling, whereas for audio, where you've got a high signal to noise, 16 to 32-bit sampling is quite common. The sample rates are a lot lower, but the number of bits is higher. So the data rates are still quite reasonably challenging for if you want to build a small, cheap recorder, but they're not, these days are not insurmountable. So for audio, you're looking at kilobits per second data rates and megabit sort of data rates for ultrasound. And as I said before, the audio signal to noise is usually much greater than 1. The two plots at the bottom show some spectrograms taken with one of the recorders I've been playing with, and you can see the bat calls right up there in the sort of 40 to 50 kilohertz range, whereas birds are right sort of down from 0 to 30. So you can it's a lot easier to separate the bats from the birds. So what have I got there? The fractional bandwidth varies, but it's the order of 20% for some types. The chirp rate, so for bats, the time between individual calls is usually around is the order of sort of 10 hertz rate, and they fly past. They don't sort of hang around, and so a bat will be audible for maybe 10 seconds. Why study bats? Well, there aren't any endangered bats in Tasmania, but there are on the mainland. But there are a number of threats to them, including wind farms. They fly into the turbines. There are some diseases emerging which are maybe affecting populations. With forestry, they lose their the hollows that they nest in or roost in. There's possible loss of habitat due to climate change, so the populations could be moving or changing. Pesticides are also an issue. And while they're not listed as threatened, they're not monitored. It's another one of these species that doesn't get monitored. In other places in the world, like the UK, £40 million per annum is spent on bats and infrastructure development, how they use the environment before, during, and after a development. So there's quite a lot of interest in understanding bats and their behaviour. So my aim was to use interferometry techniques to bioacoustics and see how well they could be adapted. The initial aims were to see how I could improve signal, if the signal to noise would improve, and then maybe see if we can find directions and distances. And if all that works, I wanted to know if it would be possible to build a device that could be easily and widely used, so that a biologist who doesn't want to or need to know about interferometry can put an instrument out there, do the recording, put it through a data pipeline, or maybe even do it on board, and extract identifications and locations. So over the past 3 years, I've been building various versions, starting off with I'm not going to go into this in much detail because I don't have much time, but starting off with a 2 microphone recorder, the Mark 1, then the Mark 2 was, and the plan for that was just to look at signal to noise improvements and see if the delay and phase could be obtained to give directions. And then a Mark 2, which had 4 microphones so that I could solve for direction totally. And now the Mark 3, which has 8 microphones, and hopefully will extract distance too. So I'm just using off-the-shelf electronics, and the data analysis is all done in Python, which is a great resource for this sort of thing. And the way that Python handles complex numbers is really nice. It makes a lot of the calculations quite simple and easy to program. And I'm using radio astronomy techniques, so things like self-calibration, phase and delay solutions, all that sort of thing, to obtain phase and amplitude against time. So this is some results. I'll quickly talk about this plot here. They're actually the same. That's my attempt at a pulsar type waterfall diagram, but this is the same data. So we've got 7 seconds of data of a bat flying overhead at our place. We get 5 out of the 8 species that are in Tasmania in our back garden, which is quite nice. But they're not out at the moment because it's too cold. So this is amplitude and frequency against time. And you can see the bat coming along, chirping away, and this is what's called a feeding buzz. So it increases its rate of calls as it's found an insect, and to find it and eat it. And this is probably when it's grabbed it here, and then flies on, still doing its ranging. These bats are called, this particular bat is a large forest bat, but it's only somewhere around about 10 grams and very small, as you can see from the photo. So these are very small creatures. Some of the data challenges I've come across very briefly. So this is one individual chirp, and I'm showing delay here in the colors. So we've got frequency on the vertical axis and time on the horizontal axis, and this is only about 70 odd milliseconds of data. And you can see what's happening is when the call arrives at the microphones, the delays are nicely behaved and smooth across the frequency band, as you'd hope. But then you get this sort of backwash. You get quite a lot of variation in phase, which is very difficult to manage. And it seems to be not a bat thing. It seems to be related to any sound. And it's so presumably some sort of instrumental effect. I haven't really got to the bottom of it. So I had to develop some routines to just pick the leading edge of these calls, which proved quite difficult. Like any interferometer, you have to worry about ambiguities and resolving them. So having a range of microphone separations is good. You can resolve the ambiguities by putting the microphones so close together that they're within a wavelength of each other. But if you've got a decent amount of frequency coverage, then you can fit for phase slope against frequency and recover delay that way and resolve ambiguity. So that's been quite a challenge. And as I've moved the microphones out, near field effects become important. And in fact, you use the near field effect to measure distance. Good things are you don't have any earth rotation to worry about. Unfortunately, there are no natural calibration sources, so you have to do your own. You can't integrate much in time because the thing you're looking at is moving and is not calling all the time, so that can be difficult if you're trying to get signal to noise. Distance measurements are proving difficult, but making some progress. So I'll skip quickly over this. You do indeed get better signal to noise improvements. You get about a factor of 2.7, and so you're actually increasing the range of your detector by about a factor of 1.6 and about a factor of 4 in volume that you're surveying. The phase is recoverable, and this is just a single baseline, which is from the Mark 1. And you can see the angle that you're measuring changing as a function of time. So that was my Mark 1 results, and that was encouraging. Mark 2, with the 4 antennas or microphones, we get direction. So this is a sky map. The top plot is the call, and the bottom plot is a map of the sky. So it's just like a normal astronomical sky map, and you can see a trace there of the direction determination. You can see the bat flying overhead and changing direction and doing some interesting things. So that was the Mark II, and this is another result from the Mark II, which is a movie, and you can see the bat moving across the sky. There's the feeding buzz there, and you can see it coincident with the feeding buzz that the bat changes direction. So it's found an insect, and it's changing its movement to track it and get it. Oops, and I'll just play that one more time, play the whole thing. So you can see some nice behavior there in that data. And the Mark III, which I'm doing now, has, I'll just skip over to that. The hardware costs are quite small. You're talking about $170 to put something together, and which is very comparable to the Audio Moth. And there it is, and you can see quite a bit of Lego there. So there are there's the inner array there of 4 microphones for short spacings and resolving ambiguities. Then you've got some intermediate baselines to give some resolution in the direction measurement. And then you've got two microphones on long baselines, which are sensitive to near field effects and give you, hopefully, direction. It's also a 3-dimensional arrangement because you don't have the advantage of earth rotation, and you want to be able to get a good range of elevations that you can measure direction and distance to. The good thing about Lego is it's modular, so you can move the microphones around and try different configurations, which is what I've been doing quite a bit. UV coverage plots, I won't stop on those except to show on the right-hand side. So this is elevation against azimuth and UV coverages. It's selections of them. And you can see, because you've got quite a good fractional bandwidth, you get quite good UV coverage in the radial direction. And the little red circle shows a one wavelength circle. So anything inside there has an unambiguous phase measurements. And distances I'm still working on. It's interesting that at near distances, I'm getting quite good measurements. Far distances, not so good. And if you look at the phase noise on a long baseline in that configuration, you can see there's a lot more, and I need to do some work on that. But that's interesting that the long baselines have bigger phase noise. It probably indicates some sort of propagation effect, and that might be, presumably that's scintillation. So scintillation rears its head once more. So what next? I want to continue on this distance measurement. The microphones I've been using are actually only rated up to 20 kilohertz, and I'm using them up to about 64 at the moment. So I need some ultrasonic microphones to better do the bats. I'm thinking about hardware processing, so FPGAs to do real-time correlation, so you get correlated data out. Maybe even some AI on board to do identifications in real time as well. There are some nice boards out there that can be used, and the Berkeley system may be a good one to use for the FPGA system. The processing needs to be more robust and move towards a complete pipeline. At the moment, it's just my own code and nobody else has to look at it. But I'd like to improve that and make it run more smoothly. There are still some more analysis techniques I want to try, like using secondary spectra, which may help with understanding turbulence effects, and may also open a new window on doing species identification from the secondary spectra. I don't think anybody's been doing that. So yeah, propagation effects, scintillation, that sort of thing. And maybe if we've got enough signal to noise, looking at reflected calls. So looking at the bats' calls reflecting off the things they're trying to catch, which would be some kind of cool. And ultimately to develop a device that can be made into something that can be used by the community. How that comes about, I don't know. So if any of that interests you, please get in touch. I'd be happy to talk, especially if you've got some ideas about using analysis techniques from things like pulsars, perhaps, or other sort of scintillation-rated things that might be useful in this case. More than happy to talk to anybody. So that's it. Thanks very much.
Thanks, Jim, for the excellent talks on such interesting topics. This application on bioacoustics are quite impressive. Any question for Jim? Please raise your hand and unmute yourself. Okay, George, you go first.
I might have missed it at the start, and wonderful talk, Jim. My question is, everything you showed, I think, was just for one bat at a given time. Is that correct? And what happens if you've got more?
I think I showed two, but yes, I did concentrate on just one call, but I've got lots. And in some cases, so that's the one that I showed about the many times, and this one is actually a different call. You can see the trajectory is different. Yeah, I mean, they were good examples. They don't always get as good as that, but there are cases where I've been in the field and I've recorded multiple bats coming over at the same time, and things get a little bit confusing. So these are sort of nice examples. But yeah, in a typical night, I might pick up a dozen good traces that I can work with.
Thanks.
Next, Bart.
Hey, Jim, that was really fascinating. Thank you. Two short questions. First one, how do the bats not confuse each other if they are transmitting and receiving on the same frequencies? And two, have you taken wind effects and temperature gradient effects in the atmosphere into account when trying to disentangle these positional information you're trying to get?
Yeah. Yes, it can. Well, it's interesting. Bats will actually change their frequencies to avoid getting confused, and they'll change the call rate as well, so that they don't get one call back before they've they don't get, you know, they don't put out 2 calls and get 1 back. They'll change their rate. They'll also some bats will call at a range of frequencies to pick up a range of scale sizes, like the one you can see there. That's quite a wide range. Others will just choose a single frequency. So they're quite adaptable. I guess. Yeah, it's interesting if they're calling at the same frequency and they're in the same range. I presume they must get confused sometimes. They're not infallible, but it's quite amazing how they adapt and modify their behaviour depending on their environment. Yes, so wind. I think wind is definitely an issue, and that may be the cause of that larger phase noise that I'm getting in that plot I showed. I think maybe still days would be better. I'm not sure how much I can do about that. I can probably measure. It can probably measure the amount of wind, and there are in fact ultrasonic sort of interferometry things that they use for wind sensors. And the other question was to do. I'm sorry, I've forgotten.
Temperature gradients in the atmosphere.
Yeah, the speed of sound changes with temperature, and that is an issue. I haven't really worried too much about that, and I think that's probably, you know, it's a sort of the 1% sort of level, and I'm not quite there with that yet. But it's quite easy to add a temperature sensor to the device and record temperature, and then you can calibrate that out. And in fact, you can do pressure too, because I think pressure is also an issue.
Well, I guess the concern in that situation was not that you would have absolute offsets or, you know, gain offsets in that sense,
yeah,
but that you would have variations across the line of sight
from
the source, the microphone.
Yeah, yeah, that's certainly going to be an issue with wind, I guess, and I haven't really quantified that. Temperature gradients, I'm not really so worried about those because it's at night, and hopefully the atmosphere is reasonably stable at night. You don't have hot and cold things in the path, and the distances we're talking about here are sort of less than 20 meters. That's about the range you can get from a microphone.
Fair enough. Yeah. Thank you.
Okay. Due to time limits, I only have the last question from John. Hi, John. Please go ahead. Hi, John. You are still on mute. No idea what's happened. If that, maybe we can wrap up now. It seems John can not unmute himself to ask question.
Oh well, just drop me an email, and I'm happy.
Yeah. John Bolton. Okay. And next week we're gonna have. Oh, he's coming back. John, do you have any question for?
Yeah,
Jim?
I looked at your system, and say PhD on electroacoustic. I don't see anything to mitigate reflections within your system. So there may be multipathing within your system and the surrounding that you might want to mitigate with some acoustic absorber.
Yeah. Okay. Thank you. Yeah, I haven't been I haven't been worrying too much about that sort of stuff, and I probably should. Yeah. I mean, there's a lot more to be done.
All right. So let's wrap up now. Next week we're gonna have Vanessa Moss to tell us practical tips for making your online meetings better. In the end, let's thank Jim for the great talk today once again. It's really nice talk. Thank you very much.
Thanks for everyone. That was fun.
Yeah.
Thank you, Jim.
Really
I'll
great.
email you.
Okay.
Yeah. So okay. Thank you everybody, and see you next week.
Thank you.
Thanks, Jim.